Okay, so you can come back to this, and I just really should just show you pictures. So what you would do is this. We're going to minimize, so lots of these optimization things. We're going to minimize this big functional, which is, we're just going to integrate over this whole region, like imagine the US. We don't want the density in a little cell, and then we want to find, well, what's the minimum distance from people in that cell to the nearest facility, right? So there are n of these, so in that case we had 5,000 for the actual example. So we just look at all the nearest ones, and of course it's, you can kind of see it visually. But it's a bit of that's a bit of an ungainly object to deal with, and of course we can't do it exactly. But there are some really clever things. So Hussein Zaid is the person who originally did something here. That paper is from 1982. And see, it's a geography piece. Yeah, awesome. All right. So you don't have to worry about the words. So basically we're going to have a cell, we're going to have a facility in it, and then there's going to be some area for that cell. And we've made a Voronoi diagram as a result of putting down, right, as we put down these, right, we're going to try our facilities. So sad. All right. We're going to try our facilities. We'll put them down. Here's we'll put boxes for facilities. We'll put them down. And then you come along and you say, well, we start to draw these lines, right? These will be part of the Voronoi cell. So anyone who's here on that side of that line will go to that facility, and they'll go to this facility, and so on. Fair enough. So that's why we end up with these cells. It's always this kind of line between, it's a bunch of lines between, that equally partition between these two facilities, right? So you construct a Voronoi diagram. And then there'll be an area in here, and let's say this is X, this is the ith one, and this is location xi. There's some area for this, and this is just some point in here, x. We'll have some area function which is constant throughout here. If that makes sense, right? So if you're any point in here, then this function is just returned. So you go to a point here and you ask this, you measure this area thing, it will just return you the area of this cell you're in. And that's a nice function to have, right? Because roughly that to a power of a half, that area to a power of a half, is going to be a measure of the typical distance from any member in that cell to the facility. So that gives us something. So we've got a distance piece. And then we do something, so that's our cost function, right? Instead of having a minimal thing in here, we're going to put this area function here. And then there's this clever thing. This is quite nice. Again, I'll skip through some other pieces. This is quite a nice thing. So we have, that's our thing we're trying to minimize. And then we realize that we can do this as well, right? So if you integrate over the whole area and you take 1 over the area, if you break this down into integrals over each little facility's region, then this is a constant in that region, and you integrate over it, so you get area over area. There would be a 1, and so you go through every region, and there are n of them. So this is a way of getting the constraint that there are n facilities. I don't know if that makes sense. So if we, right, so a of x equals a constant. This equals a constant in this shape, right? So 1 over a of x is also a constant, equals constant as well. So the integral of 1 over a of x, and let's call this like gamma of, omega I. So the integral of that thing, this is going to be dx, like that. This is, it's just whatever, let's call it, this is 1 over ai, right? It's the area of the ith. This is the ith facility's surface area. I want to write that. I want to write words. Sorry, it's embarrassing. Facilities surface area. So this will be, that's supposed to be an A. So this will be 1 over, this is just a constant. And then we just have the integral over that area, which of course is AI. 1 over AI, so that's 1. So we get 1 for each one of these regions, so we sum them up and we'll get n. So why are we doing that? It means that now we can write this down. That's the thing we're trying to minimize. This is a Lagrange multiplier type situation, and this is our constraint. We put out lambda times the constraint, so it's which we'll write as something equals 0. So it's the integral over this inverse area thing has to equal this n. All right. It's calculus of variations, lovely thing. You go through it. Essentially, you're differentiating with respect to that function a, blah, 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 and you get this result, and you get out the 2/3 relationship, right? Okay. So there's something to look at maybe later on if that is a problem we put in.